data provide. So my name is Avery, and I'm going to talk about OpenStreetMap data and how I use it with Python, and how we usually use it with Python. So first of all, who am I? Well, I'm a dude that loves maps, loves Python, loves OpenStreetMap. I work for CloudMate, I do map rendering stuff, and it just happens so that CloudMate uses a lot of OpenStreetMap data, and well, it kind of fits my interest file here. So what this talk is about? This talk is mostly about OpenStreetMap data structure and how you can use it to create map services, such as routing, rendering, geocoding, and stuff like that. So first of all, what is OpenStreetMap? Raise your hand, how many of you know what is OpenStreetMap? Oh, that's really a lot of people, so I don't know if I need this slide, but okay. So OpenStreetMap was founded in 2004 by Skip Coast and Nate Black. So they were trying to create a startup, and they came to OpenStreetMap, which is a big data provider in the UK, and they were told to get £2 million to get some data for UK. And well, those guys were just students, so they didn't have the money. So they decided to create another startup, which was to crowdsource the data and sell it to somebody. And well, what they did, they went to Isle of Man, mapped the whole Isle of Man in 3 weeks on bikes, not sleeping a lot, but drinking a lot of beer. And well, at the end, the startup failed because nobody was interested in that, and they kind of open sourced it. And it grew into a big community. Currently, it's more than 400,000 registered users. 5% of them are active members. So active member is somebody who edited at least several roads in the last month. So 16,000 active members. Just to give you a small overview, NAVTAG, the biggest data provider of map data in the world, has 4,000 members. So OpenStreetMap is 4 times that. Microsoft, MapQuest, Yahoo, and other smaller companies support OpenStreetMap, so they believe in it, so that's a good sign. And I think that's one of the most bright cross-hosting projects right now, after Wikipedia, of course. So why would we want to use OSM instead of, say, Google Maps and Services, or NAVTAG or TeleAtlas as the data provider? Well, it's fairly easy to start with, unlike NAVTAG, for example. It's of pretty good quality in Europe, and well, we're at Europe Python, so you don't care about USA. OSM sucks for USA. It has a growing community, which means that in the future you will get some support. So as the community grows, you grow the active users count, and that will help you in the future. And it's absolutely free. It's free as in beer, it's free as in speech. It's currently double licensed under 2 licenses from Creative. Share alike license, which is kind of a GPL for data, and ODBL, which is an open database license, which is a new license specifically designed for OpenStreetMap. And it's like MIT for data, MIT license. So let's get to business. So this is a cute kitty. I didn't have any images, so I decided to have kitties today in the morning. So the data of OpenStreetMap comes in different formats, but the most established one, the standard one, is unfortunately XML. It has an extension OSM, so where you see the OSM file, you can pretty much be sure that this is an XML file. There are also beta support for protocol buffers, and many third parties support extracts of OSM data in shape files, GPX files. So for those of you who work with GIS data, shape files, and GPX may sound familiar. The data itself is pretty straightforward and simple. So each object in OpenStreetMap has geometry defined in different ways for different data types, some kind of text, and changes of information. So what are tags? Well, tags are pretty much a list of key-value pairs. As I said, geometry definition differs for different data types, and change that, well, if you don't do editing on the API level, really don't care about that, so you care only about IDs. So the three data types of OpenStreetMap are nodes, weights, and relations. Nodes are pretty much just a geometric point with some tags. It may have or may not have these tags. Depending on that, we can think of a node as a geometric point or a point of interest. For example, we can map this exact photo with a point and add some tag like hotel leads and some name, Mediterranean, whatever. Way is a collection of points. So way can be used to represent such things as, for example, roads or buildings. Anything that could look on a map as a line or a polygon is represented in OpenStreetMap as a way. Relation is a collection of objects. So when you have a really complex relation, for example, when you have a street and you have buildings around it, you pretty much don't want to add a tag street equals some street name into each building. So you just create a relation between the street name and each building. And this kind of automatically makes all the buildings with the street name of the exact street. So I'm going to show you some examples from the real world. This is from Liechtenstein data. I use it because it's a small country and it's easier to parse the XML with it. So this is how a node looks in OSM data. I'm not sure if you can see it. The back rows, everything, okay, great. So the most important things for node are ID. It's latitude and longitude. So latitude and longitude are pretty much its geographic position. ID will be used later in the next slide. And as you can see, the tags here, humanity and name. So we describe this point as a bar. So it's humanity equals bar, and its name is black pearl. So it's somewhere near somewhere in Liechtenstein, I don't know where. So ways are a little bit more complex than that. So they don't have latitude and longitude, obviously. And to create geometry, we have here 5 subtags, XML childs, with tags ND, and some strange attribute ref. So ref is actually a point to node's ID. So kind of just a list of node IDs that are used to build this way. And as you can see, the tags are pretty much similar. So the tag system is very much the same for any data type in OSM. So this is a residential row with a name which I cannot pronounce. Relations are way more complex than that in XML and in the real life. So this is a very shortened example of a relation. I kind of threw out 80% of the relation, but just to show you the basics. So a relation has members, which are defined as the type of the member. It can be weight, another relation, or node. It has a reference with pretty much, we discussed in weight this. And the most important one is its role, which can differ depending on the type of the relation. So for this relation, which is, as you can see, boundary administrative, so it's actually administrative border of Liechtenstein and Austria. This boundary is composed of several ways. So instead of doing a really, really long way to denote border, several smaller ways are combined into one. So it's a pretty straightforward example. And as you can see, you can add any tag you really want. ISO 3166-1, what's that? I don't know, but somebody edited it and people use it. So let's get to importing. So that was my face when I first got to the importing. It was pretty, if someone missed it. So what are the main points when parsing OSM? Well, first of all, you have to expect faulty data. It can, some users create ways without nodes. So what is a way without node? It's nothing. It's nothing. It doesn't exist. It doesn't have geometry. Second of all, you have to parse this data iteratively. So the latest checkout of the planet data file from OpenStreetMap is 16 gigabytes zipped XML file, and when you unzip it, if you have disk space, it's actually around 240 gigabytes of data. So it's a lot of data, and you can't use elementary for that. It will, unless you work for Google and you have servers. So you have to cache extensively when doing that. Cache to RAM, cache to disk, cache to database, wherever. The order of data types is really not guaranteed by any standard, but it's de facto standard that nodes come first, then there are ways in the OSM file, and then there are relations. And IDs are unique to data types. This is a little nitpick, which bit me on my ass when I started working with that. So way and node can have the same ID. Why is that? Well, because of historic reasons, and it's not going to change. So I'm going to show you a really simple example, just a sketch of how you parse the data, how you iterate through it. Using stacks, doing simple rep projection, and creating geometries using shaking. So rep projection, just to for you to understand, we constantly use the spherical information about latitude and longitude. It's not really that useful when, for example, rendering a map. So we have to reproject it into something flat. So that's why we use rep projections. And Shapely is a very expensive geometric library written in Python, but it's actually a C-types wrapper around libDLs, which is a cool library by itself. So this is how you create projection. Don't be afraid by these 4 lines of strings. You really don't have to think about this. There is a site on the internet called spatialreference.org, and you just Google Mercator spatialreference.org, and you will get the string, and you will use it. So any projection you can think of, just look it up on the internet, and instead of doing all this crazy parameter tweaking, you won't be able to do it unless you're educated in GIS. So how do you create nodes? It's pretty straightforward. You have latitude and longitude. You reproject them, so using that projection, and create a point, which is a Shapely geometry point. So I don't think there's any hard things about this. So this is the sketch of the stacks handler. I don't know how much of you would actually use stacks, but it's not the most beautiful interface, but it works. So when we get to the node, we create a new ID, we create simple empty dictionary tags, and we create a geometry which is actually longitude and latitude. And if it's a tag, we just append this tag to our dictionary. So when we're at the end of the element, we just write it to our node's storage, which is, again, dictionary. So pretty straightforward. It goes pretty much the same for ways, and a little bit different. So I'm using a really simple here example. So instead of doing all the crazy checks, if this is a polygon or not a polygon, maybe it's a multi-line string, I'm just going to assume that this is a line string. So we don't care, it's a line string. And we have to use the previous information that we already parsed about the nodes. So when we get to the ways, we have to know about all the nodes in the OpenStreetMap file. That's quite important because sometimes nodes come after ways, and system breaker data, you can get some crazy key errors here for no reason. Well, just works this way. And again, pretty straightforward. When you get an ND tag, you just append the reference to the actual geometry. And when you get to the end of it, you parse the geometry and write it again in your ways dictionary. So this is a very short example how you can parse relations. So relations can go very different ways. This is an example how you create a relation for a multi-polygon. Multi-polygon is a polygon with some holes in it, for example, or just a set of polygons. Well, It's not pretty, but it works. And for relations, you have a lot of different ways to parse relations. You have multi-polygons, you have boundaries, you have address relations, and all that stuff I'm not going to show you here. So it's left as an exercise to you. If you want, you can do it. If you really don't want to do that, oh, by the way, yeah. So everybody's crazy about name tuples. I didn't use them here. I'm sorry, Raymond. So the idea of parsing data is pretty simple. I hope it is simple. You can use element tree if you don't have enough data to crush your server out of memory with an out of memory exception. So for example, like, I don't know, 1 gigabyte of XML is okay. 1 gigabyte of XML is actually something like San Marino or Monte Carlo, so it's not a lot of data. And you will have to stick with stacks for parsing huge excerpts, unfortunately. I hope that protocol buffer support will get out of beta, and you will be able to use protocol buffers, because as of now, you have to use stacks. Well, it sucks. That's an obvious joke, I'm sorry. I had to make it. Well, if you don't want to write your own parser, you have Osmosis, which is a Java tool. I'm not crazy about Java tools in general, but this one is really, really good. OSM2PGSQL is a really, really fast importer, so it imports the whole planet in like 7 hours. And it uses only 24 gigabytes for import, 24 gigabytes of RAM. You have also OSM to Mongo, OSM to shapefiles, OSM to GPX, OSM to OSM, which is another crazy stuff, but well, you can find all about it on the OpenStreetMap wiki. So, doing the rendering. Another funny cat I found on the internet, not related. So, what are the main principles of rendering? Well, in general, you have to know about some theory like scale, projection, how cartography works, about types of maps, but, you know, just skip the layers. So layers are the most important thing when doing rendering. They're not exactly physical layers, so I don't care about the soil under me, and nobody will when looking at your map. It's actually the layers of graphical representation. So, in general, it works like this. First, you render the Earth, some polygons like parks and everything like that. Then you render roads, then you render buildings, and then you render text. Text is special, never separated into several layers. It will never work right, and you will have problems with collision detection when doing several text layers. It's pretty hard to get right. If you are to create a rendering engine, split your data into layers, make projection configurable, so different people like to use different projections. Well, if you're aiming for web maps, you can pretty much use Google Mercator and don't worry about other stuff, just use Google Mercator. It's a pretty simple projection. Provide general way to select data sources, because even if you're using only OpenStreetMap data, some data formats are a little bit faster than the others for special kinds of tasks. So, for example, I don't know, continents rendering is better to offset to shapefiles. So, to store the data in shapefiles instead of using QuadGIS for this. And, well, don't forget about cartographers, because this is important, because what I'm going to show you next, after this slide, is when people don't think about cartographers. So this is how mapping, the rendering library created specifically for OpenStreetMap, is being used to render maps. So it's pretty straightforward. We create a map file, which is like a definition of how we render the map. Then we create the definition from an XML file. Then we create bounding blocks. So bounding blocks are geographical area that we want to render. We have to zoom to this bounding blocks, and then we just have to render this to the file. So it's pretty straightforward. Then again, style XML is not that simple. It's really full of XML. it's like my eyes are bleeding every time I edit mapping XML. It's awful. It's 2 megabytes of XML. It's not thinking about cartographers. So if you're doing cartography rendering library, don't do XML. Please don't. JSON, anything. I don't know, YAML, whatever. So I'm going to talk a little bit about mapping XML, which is still awful. So the styles and layers, the main 2 points in mapping XML. So this is a style. Style defines how the data will be rendered. And style can have several rules, or there can be several styles, etc., etc. So the rule contains several symbolizers. A symbolizer is a way to render a specific type of data. So you have line symbolizers, point symbolizer, polygon symbolizer, line string symbolizer, pattern symbolizer, around 15 as far as I remember. Each one of them has a specific set of parameters, which are defined through CSS parameter, which is a stupid name. And you can, so this is a pretty straightforward example. So polygon symbolizer will just be filled with that color, which I don't know which. A line symbolizer will get, so every line that is rendered using this style will be red with a width of 0.1 pixel. So it's going to be pretty thin. The layer, the second most important thing in mapping XML, is kind of a linking part between the style and the data source. Data source can be PostGIS, shapefiles, as we discussed previously. So for this example, it's actually a shapefile, just to simplify things. And as you can see, the layer has a projection. So this is quite important. SRS is a special reference system, so it's a projection. And for this layer, we need to know in what projection data source returns the data. So in order to get the projections right, because different projections from different data sources can mess up your map in a very unexpected ways. And you can see this file name, which is actually the link between, okay, it's actually, should be simple, not my style, but anyway. I guess the idea is simple. So, searching. Now, I have to say that I do map rendering, and the next 2 sections, I really got to ask my colleagues, and they told me how it works, so I might be wrong somewhere. If you think I'm wrong, just raise your hand and say something about it. So this is about searching. We call it joke coding. Some people call it local search. Some people call it local discovery. I prefer to call it search. It's similar to magnets in the way nobody knows how it works. And you can create either fast or correct implementation, but in general, if you're on Google, you have to choose one. Why is it hard? Well, first of all, people make mistakes when typing in. I don't know why. They should use spell checkers. The order matters. Why does it matter? For example, if you input Paris, Florida, it actually looks for this. The person who input that actually wants to see the city Paris in state Florida in his state. When you input Florida and then Paris, it's actually pretty much reversed. So people looking for, I don't know, bar Florida, hotel Florida, and Paris, France. So the order matters, unlike the web search, where the order doesn't really matter that much. Again, it doesn't always work that way, so it's unpredictable. And one place can have many names, so it's harder a little bit to index. And as I said before, one name can correspond to many places. So, I don't know, Paris, which is in Florida, Venice, which is also in Florida, I guess. New Amsterdam, which is now New York, and sometimes people call it New Amsterdam, I don't know. Bombay and Mumbai, which are pretty much the same name for the same city, but people expect it to work. And your data might not have the old name, or it might not have the new name. So people don't care about this at all. Why? I blame Google. Google doesn't care. Google just does it. I don't know. It's so frustrating. I mean, you do a lot of things to make things better than Google, and then they come up with a thing that's like 10 times better. So, I mean, we can do a simple geocoding by using some restricted subset of geocoding. So let's do the structured geocoding, for example. We have to assume some order. So say the country comes first, then zip code, the city, then the street name, then the house number. And we assume that the input is pretty much valid. So this is initial sketch of how it would look if you would start it, today. But then again, the find function would move into something like a Postgres or MySQL or Oracle query, and it would get harder and harder to keep it up. But in general, it looks like this. You just go through each input. You try to narrow the result. You try to narrow the geometry you're looking at, and at the end, you just return the geometry you had at the moment of the last actual parameter you had. This is understandable. I mean, the idea. No, well, okay. So what we really want is to fix user input. What we really want to have is a fuzzy search. Well, we can use several things for that. First one is Soundex metaphone, double metaphone, so-called phonetic algorithms. First developed in 1930, according to Wikipedia, so don't trust me. Soundex algorithm actually was kind of trying to make, if the word sounds similar, they would have the same hash code. It works for English. It works in 90% of the cases. It doesn't work for hard, long words, the words that were from Latin, from German, from Italian, from any other language. It works for English words. It doesn't really work that well for placenames, because placenames in general are not only English. So they're English only in England and maybe Scotland. So this is a simple implementation of Soundex algorithm. So as you can see, the table actually defines similar sounding consonants into unique groups. So B, F, B, V kind of sound familiar, and they have a hash code of 1. C, G, J, as far as I remember, well, there's a lot of other symbols, so 26, I decided not to do it. Most of the vowels are discarded. So in Soundex, you just return the first letter of the word, and then you have to return the 3 hash codes that come after that. For those of you who are not familiar with group by, it works like unique Unix program. So it filters out the recurring input. So if 1, 1, 2, 2, it just returns 1 and 2. So it works like that. So it's a simple sketch of Soundex algorithm. It works for English as far as I'm concerned, but it's not the most efficient algorithm. But at least it fixes something. Now the added distance is a little bit more convenient in terms of fixing the input. So it works only for 2 words, and it shows how much letters we have to change, transpose, remove, or do anything with them to get one word to be another word. And unfortunately, most geocoding requests consist of several words, so it's not really that useful. You have to split your geocoding requests into several words. And you have to split smartly, so you don't split San Francisco into San Francisco. That would be bad. Scanning database for each pair distance. So say you have like, I don't know, 200 words, 200,000 words, and you have Paris coming in with one mistake. Going through the whole database is not really a good solution. So you have to have some kind of graph for each word already in database with the added distance. I think you should check out how Peter Norvik's Eric's article, How to Write Spelling Corrector. It's a pretty good one. Article with pretty awesome piece of Python code, which explains how we can use added distance to fix the input. Another approach, the third one, and the last right now, is n-grams. N-grams are pretty much the substrings of n items and characters from the search string. So, for example, if you get something like fox and you have 2 grams, big grams, you have FO and OX for this. It's a little bit easier to index than edit distance. It gives less false positives when compared to phonetic algorithms, and the specialization of n-grams called trigrams. So the substrings of length 3 are most commonly used for fixing string input. So as far as I know, Google uses them internally. So they have smart algorithm utilizing trigrams. Unfortunately, I don't know exact algorithms, so we kind of use Postgres SQL algorithm. It's full text search, has trigrams, edit distance, soundex, and double manifold algorithms. So use Postgres and use PostJS. It's pretty cool. So this is how you create trigrams. I'm using the example from the Postgres. So what Postgres does, it adds two white spaces ahead of the string and one after. It's done to minimize the effect of small words coming in. For example, I don't know, the fox would have one trigram if we wouldn't do that. So the n-wise is pretty much stolen from the itertools recite page. A little bit configured to match the exact need. So it was pairwise, I made it n-wise. So it's pretty straightforward. How do you make the search freeform actually? You have to normalize the input. So you have to remove all the software, so-called V, A, in, near. You really don't care about that. You really don't have those words in the database, and they just pollute the database if you include them there, because near is actually a pretty common word. In general, just use existing freeform search. Solver doesn't really work for GeoSearch, so you have to stick with either PostJS or MySQL with spatial extension. You could use SpatialLite, but it's a special extension for SQLite. It's a little bit too small for big projects, but if you have something really small, your home project that you want to show your friends, then using SpatialLite is pretty much the best option you can have. And well, to do the exact correct geocoding, you have to combine rings from different sources. So something like this, where phonetic, Levenstein, and trigrams are functions that do this stuff. So they do the phosphorus, Q readings, and everything like that. So you just get all the results from each function. Each result should have some rank, so we can successfully rank it in our final rank, and we just return the highest ranked response. So, I mean, once again, Python just makes it really simple. Same thing we did in C++ for speed. It took around 200 lines, so it's a lot more to do. Getting to the last section of my talk, we're going to talk about routing. Again, we needed to explore something. Maybe it was a route home. The main issue was routing. People think that it's very simple. You know, you just build a graph, you use the X-ray algorithm, and you're done. Well, they're mostly right. But it's not that simple. You have to think a little bit more about OpenStreetMap data. It's a little bit more sparse than the usual CS101 first graphs that you were given. So The graph has to be updated often. When using OpenStreetMap data, you pretty much want to update it every week or so, because OpenStreetMap data is so high. And well, Daystar algorithm is a little bit too general for routing on the road data. A-star, which I hope some of you have heard about, is no better for road data. So you have to come up with a more sophisticated solution. And to add to that, routing is not only a technical problem. Some people expect different results for the same start and end points. And this is something that you can't really control, and you just have to select one exact way of doing routing. And routing through cities, even if it gives you 2 times better result, is a little bit annoying. People don't like when routed through cities. So in our first routing implementation, our algorithm just didn't care about if the route goes through a city or it goes through a highway. And then people started complaining that, well, this route goes through a city. I know that it is faster, but I get annoyed by riding through the city. I get annoyed by pedestrians. I get annoyed by another car riding right of me or left of me. And, well, it makes your algorithm a little bit harder, and it makes your graph a little bit harder to create. So, as I said, OpenStreetMap data is a little bit sparse, so adjacency metrics is not really space efficient for this task. Graph representation has to be very common. But if you're starting out with OpenStreetMap data and just want to, simple routing library, you could use NetworkX or iGraph. They're pretty good. Both have C extensions. Actually, iGraph is a C library with Python wrapper. NetworkX has C extensions for speed. So I'm going to use NetworkX as an example. And again, it's simple with OpenStreetMap. It's simple. You have to import graph. You have to import the shortest path function. Building graph, you just go through each way. You iterate in segments. So each way consists of, for example, each way consists of several segments, and you have to iterate through them. You just add the edge. Before that, you have to somehow calculate the weight of this edge. So, for example, for residential roads, you probably don't want to route through residential areas, unless you're pretty much required to, so unless you want to get home. So it should be a little small coefficient for the residential roads, and it has to be pretty much huge coefficient for motorways, for example, because, well, motorways are fast. And then you just build the shortest path. I've tried it out yesterday. Well, NetworkX worked for me, and on Liechtenstein data once again, but it worked. But in general, in practice, there is no silver bullet. iGraph won't help you. NetworkX will need 20 gigabytes of RAM for Eurofaster. And well, I killed it before it stopped working. So I guess it would be more than 20 gigabytes. Splitting data into country graphs might help. It will help if your servers or your library is kind of targeting the smaller communities. But if you want to do the whole Europe routing, joining the graphs on the fly will get you in a trouble because it's really, really slow. As an example, our in-house C++ graph library requires 20 gigabytes of memory for the whole world. It's very efficient. Our previous implementation requires 45 gigabytes of memory for the whole world. So you really have to, well, first of all, it's amazing because it's a lot of data and it's a fun project to do. And second of all, you have to understand that this is really, really hard. But it's fun. As an option, you might consider using feature routing. It's easier to start with. There is an existing importer from OSM data. Well, we couldn't make it really fast, unfortunately, and it's harder to configure the coefficients with which you import the data into the graph, so it didn't really work for us. Neo4j, last we tried it 2 years ago. Neo4j team worked with us consistently, and well, they didn't deliver any good results. For those of you who don't know, Neo4j is a graph database, another NoSQL branch of databases. If you're doing serious business, so if you get into OpenStreetMap in a serious way, you will have to eat your own dog food and create your own C++ library. There is only one efficient open source implementation of OpenStreetMap graph routing. It's called contraction hierarchies. It works pretty good, but it comes update data on the fly. So you have to re-import every week or so. Each time you update the data, you have to re-import the full graph. And it takes around 2 days to import an whole graph. So if you're at work, and I'm pretty sure you are, I'm done. Just some highlights. So I advise you to use OpenStreetMap data. It's easy, and well, try building something simple. It's pretty cool when you get it's done. Try building something cool because it's simple. And well, Python is like awesome. So do it in Python, and well, for GIS, it's like the second best language after C++. C++ is awful. Do you have questions? We need a microphone, I guess. Yeah, we're gonna work the microphone.
Thank you. I was just hit by my own back.
Okay.
So, I think there are quite a lot of questions. Okay, let's go this side first, then you can just pass the microphone on.
Small correction regarding the search. Solar supports spatial search. I think the new version is built in, and for older versions, there was a plugin that could be used for that.
Well, I have to ask for it, but I think we evaluated solar and it didn't really work for us. I don't know why. So I'm the map rendering guy, so I didn't know the exact thing that happened with solar, but I think it's a pretty cool library. I'm using it in some side projects. If it does spatial queries, then it's great. I mean, it's one of the most cool projects out there with regards to freeform search.
And one question, what would you say is currently the best method, the fastest method with limited resources and memory to import parts of OSM and render files for webinars?
Okay. This is a pretty
Postgres or maybe MongoDB offers a faster solution by caching the database instead of
yeah. So MongoDB, I've tried to use it. Didn't really work out. Right now, they're trying to add spatial support. I hope it gets a little bit better. Right now, it doesn't do ref projections, for example, so it's not really that useful for us. PostGIS is still the best spatial database out there if you're looking for free databases, because if you have money, you can use Oracle. But I mean, in general, OSM GSPL can import in so-called slim mode, where it uses no long memory, and it imports to PostGIS. So I guess the best way right now is OSM GSPL and PostGIS, and using mapping for it.
Okay, for routing, you don't need just a graph, because you have also signs, so you can not turn left or turn right.
Right.
Can you take it into account, and is this information in OpenStreetMap?
Yes. There is a relation called turn restriction. So we do this, and we did this for 2 years already. And the open source library, construction hierarchies, does it too. So it's pretty much built into OpenStreetMap. So, and most editors support editing the turn restrictions in OpenStreetMap. So it is supported. It's a little bit easier, I think, in MapTech data to use turn restrictions, but OSM is pretty good in this regard.
Another question?
Yeah.
So just to pass the mic.
I have a question about internationalization of the user data for the OpenStreetMap, because when you were doing the XML at the beginning, there were some words who were at least not in their original language.
You're talking about relations, right?
I'm talking about nodes.
Well, the example was with this one, right?
This one.
So you're talking about internalization. You can see it right here. So mostly it's done through name. So name should be in the local language. So for Liechtenstein, I think it's German. But if you want, there is actually a name semicolon EM for English name. There is name semicolon RU for Russian, and et cetera, et cetera. So this boundary has around 20 different names in different languages. So, but the general rendering on the OpenStreetMap doesn't use this tag, so it renders only name tag, which is in the local language. But if you get the data, you pretty much get data in different languages. So the names are generally in different languages. Names of countries, some streets, etc., etc. So it's a global database with internalization built in. One more question.
What's your position on the purpose of OpenStreetMap data? Doing a model mapping of it, and there's kind of this tension between people who do it for the render and people who do it for the routing and people who do it for the conceptual correctness.
That's a political question.
What do you think about it?
I don't care. I meant for myself. I mean, that's the beauty of OpenStreetMap. You can do whatever you want. But at the same time, it's a problem for OpenStreetMap because everybody does whatever he wants to. And well, there is a general consensus that you shouldn't map for the renderer. The consensus between the old members of OpenStreetMap, when the new members come in and they see that, well, their golf course isn't rendered at all, and they map it not as a golf course but as a park, for example. It's wrong. It's generally wrong, and the data itself is getting worse because of that. So my view is that you shouldn't tag for the renderer. As for tagging for the router or the geocoding, I think it's pretty much fine. So it's the data that people don't see, but they will get the relevant data when searching for it. But again, it's a political question, which I think cannot be answered by one person from a community. It's like something community has to agree with. So, does anybody have questions? All right.
Thank you, and